I'm Naoki Ishibashi. I talk about evaluation of performance of sparse clarification algorithm based on orthonorm optimization. Recently, because measurement technique has been developed, it is easy to get a data of high dimensionality. In the study of neuroscience, we measure the human brain activity with the functional magnetic resonance imaging. However, because of limitations of the experimental costs and time, the sample size is small. The small sample size declines generalization performance by overfitting, so we presume that important features explaining brain activity are few. That is sparse algorithm. The algorithm selecting important features makes performance more good. And one has high feature selection performance can detect important brain areas. One method of optimizing feature value is orthonorm. Orthonorm means number of feature values. It can be written like this formula. Orthonorm can decide important or not important for each feature. However, orthonorm optimization usually takes huge calculation costs. For example, m-dimension data combinations are 2 to n-1 patterns. To avoid this problem, previous study made sparse clarification algorithm based on orthonorm optimization. Iterative hard thresholding for clarification, IHTC. IHTC deals with two-class discriminant problem. In two-class discriminant problem, we have data vector and class label for training parameter vector. IHTC is based on the iteration algorithm described here. And the parameter vector is recomputed in every iteration. HK is a threshold function which allows to make the parameter vector sparse by selecting the parameters corresponding to minimal residual error. There is an image when IHTC analyzes 4-dimensional data. Here IHTC selected 2 features. In previous study, it was not being clear whether IHTC is more suitable for analyzing different sparse data like fMRI scan data. So in this study, we evaluate IHTC performance in analyzing different sparse data. We could define 2 performance values. One was the predicted performance obtained from classification. The other was a generalized performance expressed by kappa values. Kappa statistics are means of selection performance measure for future values. A bigger kappa statistics value means a better selection. Moreover, we also got predict performance and kappa values in simulation by sparse logistic regression (SLR) and support vector machine (SVM). Firstly, we made feature vector. This vector has 2 classes, 1000 dimension and 440 sample size. Then we made feature vectors which have 22 conditions of non-zero feature values. Secondly, we made noise vector. Noise vectors have 10 conditions. Dataset vectors were made by combining each feature vector and each noise. To compare the 3 methods' performance with the analysis of variance ANOVA. To find out if the results of a survey or an experiment are significant, we reverse the p-values with the Bonferroni correction. These are each classifier's predicted performance. Horizontal axis means noise rate. Vertical axis means predicted performance. Left figure conditions is sparser than right one. Markers denote the mean and error bars denote the standard error. The dotted line shows the chance level. When the future vector sparsity is high, IHCC and SLR's predicted performance tended to excel SVMO. On the other hand, when the sparsity is low, the three classifiers' performance was nearly equal. These are each classifier's generalized performance. Horizontal axis means noise rate. Vertical axis means generalized performance, kappa values. Left figure conditions is sparser than right one. Markers denote the mean and error bars denote the standard error. As for the future selection performance, changing sparsity and difference of noise ratios affected the future selection performance of IHCC and SLR. The kappa value IHCC was significantly higher than that of SLR. As a result, for three-way ANOVA, both the predicted performance as well as the kappa values were influenced by the kind of classification, sparsity, and noise ratio. The simulation results suggested that IHCC is more suitable than SLR and SVM to analyze small sample size and high dimension data. We conclude that it is the optimization made which leads to higher performance of the IHCC compared to SLR. In this study, we have added independent and identically distributed noise, IID noise, to the artificial data. However, fMRI scan data usually have correlations between different voxel areas. In the future, we will try to analyze the data with correlation between different brain areas. Through analyzing real brain scan data with IHCC and other models, we want to evaluate the performance of IHCCs and suitable conditions for using it. This is a summary of my presentation. Thank you.